magnesium carbonate. Carbonates are all insoluble except for group 1 and ammonium, so this will be solid. And then acids are going to be aqueous. And this is going to yield what? It's going to yield magnesium chloride plus carbonic acid. And then we know carbonic acid is unstable and decomposes into H2O liquid and CO2. The state for CO2, it depends on the rules for molecular compounds. For the rules for molecular compounds, CO2 is what we call nonpolar, and H2O is polar. And so what we need like to dissolve like. We're going to talk about nonpolar and polar later when we get to structure, but these are unlike. And so most of the CO2, like 99.9% of it, will bubble out of the water. Maybe about 0.1 or less percent will dissolve in the water. Depends on how much CO2 we have. You can actually get quite a bit of CO2 in water by forcing it in. Like if this were sparkling water, you put pure CO2 here. If you have pure CO2 here, then more CO2 can dissolve. And so you can actually get quite a bit of CO2 in there. But if this is just air, then the amount of CO2 in air is very small. And therefore, we're going to get very little CO2 in water. And so this is not sparkling water, because the CO2 in the air, barely any dissolves in here. And so, anyway, this is just a typo. I think it should be Gauss. You're right, this is wrong. If they put aqueous, that's wrong. Chloride, bromides, and iodides are soluble except for silver, lead, and mercury. So this is aqueous, that's okay. And we'll be balanced, of course.
They also have magnesium carbonate as aqueous in this problem. That would be incorrect, right?
That would be incorrect. Sodium carbonate, yes. Ammonium carbonate, potassium carbonate, any of the group 1 carbonates, lithium, but not magnesium. Yeah. Magnesium carbonate is what they call dolomite. Dolomite, it's a rock. Using dolomite here. Calcium and magnesium carbonate. This is not pure. It's a mix. This is what we call mixed cation salt. Calcium and magnesium are in the same family, and so they can behave similarly. Substituting them. Let's see, there's probably something that's pure magnesium carbonate. But the dolomites, this is not, when it rains, the mountains don't dissolve away. A little bit does dissolve away, but this is just centuries. And so this is wrong. Magnesium carbonate is solid. No, not aqueous. But sometimes that happens in the books. Even though, what edition is this?
Mine is the 7th edition.
7th edition. So that's by 7th edition. 7th edition, they still haven't caught all the typos. And so that happens. Even with the 11th edition of some books, there's still things. And so they hired all these editors to catch this, but a lot of the editors don't know much of something. And then things start to blur when you look at so many pages. But anyway, this is what we call the total formula. I call it the complete equation, CE, the complete equation. And then we want to be able to do the IE. This is important, because if it's an insoluble salt, it doesn't dissociate into ions. But a strong acid like this will dissociate into the ions, 2H plus 2 chloride. This is a soluble salt, so this dissociates into the ions. And water, non-electrolyte, and CO2 is another electrolyte. Yes, so we just leave that. In this case, chlorides would be the spectators here. And so the NIE for this is the magnesium carbonate solid will be attacked by the acid. It could be attacked by any acid. Any acid will give H plus, which can dissolve this, or magnesium 2 plus H2O liquid plus CO2 gas. The driving force for this, we say, is just gas formation or effervescence. Usually we do the driving force right at the beginning. There's also another driving force, and that is HCl going to carbonic acid. Carbonic acid is a much weaker acid than HCl. And so we're going from stronger acid to weaker acid as well. Even though the weaker acid decomposes, it turns out that CO2 is asleep as well. If you don't exhale enough CO2, then your blood pH can change. You become acidic. Your blood pH has to be maintained at a very somewhat precise level. If it's too acidic or too basic, that causes problems. Okay, other questions?
Number 63, also chapter 9 from that. This one had, it was going from a weaker acid to a stronger acid, so I knew that it couldn't be, like, it had to have, like, a different equation, like it was an exception to the regular double replacement, but I don't really know where to go.
Well, it could go from weaker to stronger acid as long as there's one driving force. There needs to be at least one driving force present. And so maybe there was another driving force that could have driven it. And so the question is, if you're going from weaker to stronger, then you would say NR, no double replacement reaction. But let's take a look at it. Number 63.
Yeah.
Hydrochloric acid is poured into a solution of sodium hydrogen sulfide. So hydrochloric acid, HCl, HQ plus sodium hydrogen sulfide. Sodium hydrogen sulfide is, well, it's the sodium ion plus the hydrogen sulfide. So if we know what sulfide is SO3 2 minus, and then we add an H plus to that, and that's going to change it to HSO3 minus. And so sodium hydrogen sulfide is just NaHSO3. This is also called sodium bisulfite. And so what we're going to have is hydrogen sulfide. Hydrogen sulfide is called what? Is that sulfuric acid or
Sulfurous.
sulfurous acid? And sodium chloride. Sodium chloride would be NaCl. First, let's take a look at the driving force for this. So I think it's just an acid position here. Is sulfurous one of the 7 strong acids?
No, it's sulfuric.
No, but hydrochloric is. And so this is actually, if it were sulfuric acid, that would be a different story.
Yeah.
And so it was just because of sulfurous or sulfuric. So it's going from stronger acid to weaker acid. That's one of those. And there's one other situation here. I can write all the gas formulas in double replacement. There are 3 driving forces for double replacement that we look for. What are the 3 driving forces?
Gas formation.
Gas formation.
Precipitate.
And
Stronger acid to weaker acid.
stronger to weaker acid. So we just saw carbonic acid. Carbonic acid spontaneously decomposes into H2O liquid with CO2 gas. So this is definitely a gas former. But there are 3 that people have to memorize. So this is 1, 2. 2 is sulfurous acid. Sulfurous acid, like carbonic acid, is not so stable. And so sulfurous acid decomposes into what? What do you think it decomposes into? It decomposes into H2O liquid and sulfur oxide. Well then, which oxide of sulfur? There are many oxides of sulfur. Like, there's carbon monoxide, carbon dioxide, there's sulfur monoxide, sulfur dioxide. It would be sulfur dioxide. Yeah. Sulfur dioxide is a gas. It will just bubble out. Sulfur dioxide is a poisonous gas. So you would want to be careful in this particular reaction because if you form sulfurous acid, you're going to form some sulfur dioxide, which is toxic. You wouldn't want to do this on the bench top. You want to do this inside the hood. The third one is when we form ammonium hydroxide. So if we have ammoniums and hydroxides combining, this decomposes into ammonia and water. Now ammonia is different than carbon dioxide and sulfur dioxide. Carbon dioxide and sulfur dioxide aren't very soluble in water, but ammonia is quite soluble in water. And so when something's quite soluble in water, we call it aqueous because ammonia is like water in certain respects, or gas. You can smell the gas. And so there'll be a little bit of gas formation here in this. 4, there are other ones like HCN. If you have hydrogen and cyanide, they come together to form HCN gas, H2S, hydrogen ions and sulfide ions will make H2S gas, etc. So there are a bunch of others that form gases. But those are the main gas forming reactions here. Yeah, the supplement had the double replacement reaction in the supplement and some of the other reactions are just too much. Should just do some simpler ones.
I also noticed the book likes to change the order of the net ionic equation as the final. So
Yeah, usually they'll try to put the cation first and then the anion next. It doesn't matter, but maybe it's good because the cations are usually written first, followed by the anion. So I probably should have changed the order myself. I just left it.
So if you have an elemental solid, would that come first before the cation?
Yeah, to get it in the pattern. If you have an elemental solid, you write that because you want it to go in A plus BX pattern.
Mm-hmm.
And so I would have reversed that. I would, if they put the element second, I'd probably reverse it to get the A plus BX pattern. It doesn't matter which order you write these in, or whatever is most convenient. Right. So that's what they did.
Yeah, because I noticed during the total ionic equation, obviously it can be fully expanded out and,
Oh yeah, yeah. In that case, it also doesn't matter. Like, let's see, let's go to the ionic equation of the total. I just say ionic equation. I get rid of the total. So I call this the complete equation, the ionic equation, and net ionic equation. And so HCl we already saw. Is this balanced? Yeah, this is balanced. So H plus plus Cl minus. This is going to be aqueous. Now this is aqueous too, but this decomposes. So I usually draw an arrow here, crossing it out and replacing it with the decomposition product, H2O liquid plus sulfur dioxide. Yeah. Now if I form two H2SO3s, then I double everything. This has to go in the first equation. A lot of people get mixed up and they think, oh, I'll write that in the ionic equation. No, all three equations have to be the same. The same products, same reactants. You can't have one reactant that is H2SO3 in the first one, and then a second, product is a product on the right side. A second product on the second one. No, it's got to be all three have to be the same. Now, how does sodium hydrogen sulfide split?
Sodium ion by sulfide.
Yeah. Sodium ions and hydrogen sulfide. Now, hydrogen sulfide, the hydrogen stays on there because it's not one of the 7 common strong acids. If it were one of the 7 common strong acids, you break off the hydrogen. But since this is weak, this is an acid anion that's weak, we leave the hydrogen on there. It's stuck on there, so just leave it. And so this is going to form H2O liquid plus sulfur dioxide gas. And again, since aqueous is the most common state, I'll just omit the aqueous and write liquid and gas and solid as they occur. Sodium ions and chloride ions. This one, the sodium ions are spectators, and chloride ions are spectators. Normally, a lot of people cross it out. I just underline it because this is a useful equation. No, it's not the net ionic that we're always after. Sometimes we want to know the ionic equation to see all the species present. Okay. So this is going to effervesce. Now we'll have gas formation here. Also, we're going to have stronger acid, weaker acid. And so this would be the net ion equation here. In this case, if the anion were first, I might, flip it because it's just nice to have the cation on the left and the anion on the right. Sometimes the anion ends up on the left and the cation on the right. So the book's just trying to get into that format like this. So this would be another double replacement reaction. Okay, other questions?
Can we do a no reaction one?
Yeah.
For instance, number 73.
Okay.
Silver solid plus hydrochloric acid. That's aqueous, obviously.
Yeah. The HCl is going to be aqueous, but I'll just leave it off. See, writing. This one, if it were reversed, like hydrochloric acid plus silver solid, I just flip it. So I get it in A plus BX pattern. This is going to give us AX. So A is silver, X is chloride. So we'll have silver chloride. But, this silver is different than this silver here. How so? these two silvers aren't the same. Because this is silver metal, and this is silver ion. And so a lot of people are tempted to write silver ion here because it's silver ion over there, but no. This is what we call oxidation reduction reaction or redox reaction, which somebody loses electrons, somebody else gains electrons. And this hydrogen and this hydrogen are clearly different. What's the A plus BX yields AX plus B. B is hydrogen, like that. But this is the element hydrogen. That's a hydrogen cation. The element hydrogen likes to be diatomic, like this. Hydrogen, what's the state on hydrogen? Gas. So, the question is this driving force? Gas formation.
No, it's not double replacement.
Right. That's good. You catch that? This is not driving force. Why? Because this is not a double replacement reaction. This is a driving force for double replacement reactions. This is not a driving force for single replacement reactions. Single replacement reactions have a different driving force. What is that driving force?
The activity series.
The activity series. And so what is more stable? What's more reactive, silver or hydrogen? You know? Which one do you think is more stable, less reactive, silver metal or hydrogen gas? Yeah, we don't even need to consult. Do you need to consult the activity series for that? I mean, is it clear that silver is a lot less reactive than hydrogen? Yeah. If you had a cylinder of hydrogen gas, you'd have all kinds of warnings on it. You know, it's explosive. But, you know, when you have silver quarters, there's no warning on that it's explosive, because it's not explosive. Really. Not in the sense that silver is. And so the this one would be going from a more stable, that is less what we call active, from the activity series, less active is more stable, to more active. This is the driving force. The driving force is we want to go from more active to less active. And so it turns out the downhill direction is reversed here. And so the driving force is actually backwards here. Therefore, in the forward direction, what we say is that there's NR for single replacement. When we have NR for single replacement, we might think about alternative patterns. So in this particular case, we might consider this. Silver is going to lose electrons if we want 4. Silver would lose electrons to which of these species here?
Fluoride.
Chloride would gain it?
Oh no.
No, chloride's a spectator. It doesn't change. Who would gain it?
Hydrogen.
Hydrogen ions. So that's the A plus BX pattern. So one thing we got to worry about is maybe hydrogen ion isn't the best oxidizer present. Is chloride a good oxidizer? No, actually chloride isn't even on the oxidizer side of the chart. When we look at this, I see chloride here. Actually, this is chlorine. Chlorine's a good oxidizer, but chloride is a pretty poor oxidizer. In fact, it isn't even an oxidizer. It's on the reducer side of the chart. And so far, H plus is a stronger oxidizer than chloride. Then we have to think about water. is water, which is the solvent because this is aqueous, is water a better oxidizer than H plus or a better reducer? If nothing worked out here, maybe we have it assigned wrong. So we think in terms of the chart method. Thinking in terms of the chart method, we look for the strongest oxidizer and strongest reducer present. And so the two reducers that are present are silver and chloride and water. So the three reducers present, sorry, miscount there. Silver, which is here. Water, which is here, and chloride, which is here. So the best reducer is silver. Well, that's fine because that's what single replacement should be. Silver should be the reducer. Now, as far as oxidizers go, we just have H plus and water. And so as far as oxidizer, H plus is here. And you see these three dots? Yeah. That's where water goes as an oxidizer. And so these three dots mean water. And so H plus is better. So single replacement, this should fit the single replacement form, and then there's no reaction here. Here, in that case, if there's no reaction, then there's no reason to do the ionic equation and the net ionic equation for this. Okay, other questions?
Yeah, so in any of these problems, because I noticed there wasn't at least an example in our homework, but I take it that a hydrate can't be involved in any of this.
Hydrates can be involved. Hydrates will be more like Chem 1A. I mean, it's pretty simple actually what you do. With a hydrate. First, hydrates are usually water soluble. When you have water soluble hydrate, what happens is all the water that's trapped in the lattice gets released because you pull apart the ions in the hydrate, and then that frees up the water. And so it turns out if you have a hydrate, you treat it just the same as the other compounds. But you really aren't going to have to worry about that in 4. In fact, I was trying to keep this maybe simpler, but the book does have harder problems. Simpler so I can put some reactions on the test. Like these. I'll have a double replacement reaction on the test. You recognize all these as being AB plus CD pattern. Does that look right? Like this. What's this called here? Lead 2 nitrate plus
potassium iodide.
So lead 2 nitrate plus potassium iodide forms lead 2
Iodide.
and potassium. So this one, cobalt 2 nitrate plus. So that's going to produce cobalt 2 phosphate and potassium nitrate. People see the numbers there and then they get all mixed up, but we don't care what the numbers are. We'll balance everything at the end. So if we're forming cobalt 2-phosphate, you know, then I just look, you know, how many cobalt 2s do I need for each phosphate? This often works, you know, as a quick way of doing it. We just use these as a subscript here. And so I'll need 3 cobalt and 2 phosphates. So that would be cobalt 2 phosphate. Phosphates, carbonates, and chromates are all insoluble except for group 1 and ammonium. Well, cobalt's not a group 1. And therefore, this is insoluble. So this is going to precipitate. The precipitated cobalt 2 phosphate. Potassium nitrate, a lot of people do this because they want to try to keep things balanced. K3NO3, but this is not potassium nitrate. If we want to keep things balanced, we'll worry about it at the end. So if we need 3 of these, we'll put 3 in the front here, or whatever. It might be more. I think it's 6 actually, how many we need to balance it. So don't get caught up doing that kind of stuff. This computer is very sorry. What's this called?
Potassium.
Potassium chlorate and nitrate. Nitrate, right? Nitrate, yeah. Potassium chlorate and magnesium nitrate. This is going to form potassium nitrite and magnesium chloride. Did you get a driving force for this one? Everyone? Anybody? So if we're looking at potassium chlorate plus magnesium nitrite, we're going to have potassium nitrite like this, and it's 1-to-1. Potassium is plus 1, nitrite is minus 1. And magnesium chlorate. Magnesium chlorate is going to be a 1-to-2. 2 chlorate for every magnesium because chlorate's minus 1. So all group 1 salts are soluble, correct? Well, what about chlorates? Chlorates and what else? Chlorates. Perchlorate, yeah, you probably can throw that in there, but there's one that it just says chlorates and nitrates and not bicarbonate. Chlorates, nitrates, and acetates are all soluble. So there's no precipitate here. Do these decompose into gas? No. Are we going from a stronger acid to weaker acid? No. So actually, this one has no driving force. So there's no driving force. Therefore, NR for double replacement. No reaction for double replacement. In this case, if we were to do the ionic equation, this is the complete equation, but if we were to do the ionic equation, it would look something like this. We'd have potassium ions, chlorine ions, magnesium ions, nitrite ions, going to, actually I'm going to balance this now. 2, 2. Potassium ions, nitrite ions, magnesium ions, and chloride ions. We'll balance it. 2, 2, 1, 2, 2, 2, 1, 2. 2, 1, 2, 1. 2, 1, 2, 1. Yeah. That's it. And then down here. What's the spectators here? They're all spectators, so everything cancels out. There's no net ion equation. So And if you mix these two solutions together, you just have a mix of all these ions. They don't do anything. In other words, they don't react with one another. So everything cancels. And so this would be an example of a no reaction for double replacement, number 31.
So when everything cancels, then it's no reaction.
Yeah. Or there's no driving force. We looked at there's no driving force here. Okay. What's this next one called here?
Barium
Barium
nitrate.
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 And is that iron 2 or iron 3 sulfate? It's actually iron 3 because what I'm going to do is I'm going to do the reverse. Sulfate is a -2, so we'll reverse this. Put the 2 over here and the 3 over here. And so that's a quick way to tell the charge. It doesn't always work because sometimes the ratios are simplified. But if it works. So in other words, I'll move the 2 up on sulfate as the charge, -2, and the 3 up on iron. So this is iron 3 sulfate. And so this is going to make barium sulfate. Sulfates are all soluble except for which ones? Sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. So this is going to precipitate. Barium sulfate will precipitate, and we're going to form iron 3 nitrate. Iron 3 nitrate is soluble. All nitrates are soluble. So we're going to precipitate a barium sulfate in this one, and we're going to have a driving force. That's all we need is one driving force. Let's go to this next one. This is silver nitrate and silver nitrate and lithium bromide. It's going to give us silver bromide. Bromides, chlorides, and iodides are all soluble except for
Silver, lead 2, mercury 1.
Yeah, silver, lead 2, mercury 1. And so silver bromide will precipitate. It's insoluble. So we'll get a precipitated silver bromide. And then lithium nitrate, all nitrates are soluble. So that's not going to do anything there, but silver bromide will. And so there's a driving force here for 33. 34, what's this one here? Nickel 2 bromide, where we can do the charge thing to bring it up. Nickel 2 bromide. And so this is going to yield nickel 2 hydroxide. Hydroxides are all insoluble except for group 1, ammonium, calcium, strontium, barium. So this is not one of the exceptions. So nickel 2 hydroxide will precipitate. It's kind of a green precipitate. And so nickel 2 hydroxide precipitate, and we're going to get potassium bromide. Potassium, all group 1 soluble, so that's not going to precipitate. How about this one? Zinc chloride and sodium sulfate or sulfite? Sodium sulfite. Yeah. So this is going to give us zinc sulfite. Now, do you have solubility rules for sulfites? No, we didn't. So one thing we could try is we could assume that the sulfite is going to have similar solubility as sulfates. If we assume that sulfites and sulfates are similar, then zinc sulfite should be soluble because sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. So this should be soluble. And sodium chloride. Now, sodium chloride is not going to be a driving force. So the situation is this. Some of these other things like fluorides, they have a lot more exceptions. So things that have a lot more exceptions is probably not worth memorizing because you're going to overload it. And so what we do is we just look it up. And so if we're curious about zinc sulfite, we would just look it up to see what the solubility is. Obviously, you can't do this on exam, so you probably assume, you assume. This is a different. Chem. This is from the NIH library. Do they have it on Wikipedia? Wikipedia has it in a nice format. No, it's not on Wikipedia. The nice thing about Wikipedia is it has this little table here. And in this table, it'll tell us the solubility in water. So for example, here, if we look at zinc sulfate, not zinc sulfide, zinc sulfate is pretty soluble in water. We can dissolve 57.7 grams in 100 milliliters of water. 57.7 grams makes zinc sulfate even more soluble than sodium chloride. Sodium chloride you can only dissolve about 36 grams in 100 milliliters, so this is very soluble. So we'll send that zinc sulfide is similar to zinc sulfate in terms of solubility, or we'll look in PubMed or PubChem if they have solubility data here. Usually they have physical and some chemical properties in these. Zinc sulfide, this has a Wikipedia page for zinc sulfide. If you're at the library, we have three sources that are in books that you can look at. The three sources that are in books, the main book that people use is called the CRC Handbook of Chemistry and Physics. Yeah. CRC Handbook of Chemistry and Physics is revised every year. So what edition are we on? Like we're on the 103rd edition, maybe? Only 18 left. Yeah, we're on the 103rd edition of the CRC Handbook. So they update the data. This is a really useful book to have. CRC Handbook of Chemistry and Physics. It's expensive. Well, I guess it's not that expensive now. It used to be. I used to think of this as really expensive. But it's always been a couple of $100, the CRC Handbook. And it stayed this way for decades. If this inflated like textbook prices, then this would be like $1,000 now. These textbooks used to be reasonable too. I think I paid like $30 for a textbook. That's one. The other one is, I wonder if we could see inside this. I can't see it. You can buy older editions. They're pretty cheap. The other one is called the Merck Index. The Merck Index has more of a biological and natural products. CRC has a lot of more inorganic. And the Merck Index is good too. Wow, this is really cheap, 25. Oh, it's brand. Encyclopedia of Chemicals, Drugs, and Biologicals. And then there's the Encyclopedia of Chemistry. which we have in the library. So the Merck Index, the CRC, and the Chemical Encyclopedia all should be in the library. So if that's the case, if we say that zinc sulfide is soluble, I'm going to look at here. I think they got these out of order. Where were we at earlier? Well, anyway, in problem number 76, they say sulfides follow the same solubility guidelines as sulfates. I'm going to assume that. And so if that's the case, what number was that? If that's the case, then there's no driving force for this. You see, because there's no precipitate, zinc sulfide soluble, sodium chloride soluble. There's no gas, and there's no acid here. And therefore, there's no reaction in number 35. So that was another no reaction here. How about 36? What do we have here? We have sodium nitrate and barium hydroxide. Now, barium hydroxide is one of the exceptions. Most hydroxides are insoluble, so it's typically solid, but barium, what is it? What were the hydroxides again? Hydroxides are all insoluble except for group one, ammonium, and calcium. And so this is one of the exceptions. This is a soluble hydroxide. Soluble hydroxides are also strong bases, so this is a strong base. When I look at that, the base is kind of the opposite of the acid. If you have a strong acid, it's pretty reactive. If you have a strong base, it's also pretty reactive. And so we're careful with strong bases here because they're fairly reactive. So this is going to produce sodium. Sodium hydroxide is a soluble hydroxide, so no precipitate. And barium nitrate. All nitrate salts are soluble, so there's no precipitate. And then are we going from a stronger acid to weaker acid? No, and we're going from a strong base, barium hydroxide, to another strong base. Sodium hydroxide is the most common strong base that we use in the laboratory. And so 36 has no reaction. There's no driving force for 36 as well. So that's it. (37) Write the net ionic equations for the precipitation of each. So this one is just lead ions, lead 2 ions combining with carbonate. This is calcium combining with hydroxide. Except calcium hydroxide, wasn't that one of our hydroxides are all insoluble except for group 1, ammonium, calcium, strontium, and barium. And so, in something like this, kind of violates that. But what you have to realize is that there are, eventually you can get something to precipitate. I mean, if you keep adding, it's not infinitely soluble. Things aren't. And so, for example, sodium chloride, we can get about 36 grams to 100 milliliters, but if you try to force 37, it's not going to happen. And so we end up with some salt left over. And so there's a little bit of gray area in there. But I would say calcium hydroxide is soluble, not insoluble. Let me show you something here. Have you ever heard of chelation therapy? Like lead. They used to use lead pipes. Lead's fairly unreactive, I guess. Lead pipe and lead paint. You heard of that? Lead. Well, actually, let's talk about a couple of things here first. Some of the solubility. Sodium hydroxide is good at like reacting with fats and oils. Have you heard of that? It's a process where sodium hydroxide can break apart fats and create fatty acids. And those fatty acids will probably be easier to drain, perhaps, or that kind of thing. And so sodium hydroxide, you know what one of the uses for sodium hydroxide is? You can buy it at the supermarket. It's called, which consists of solid sodium hydroxide. And do you know what they use lye for? Use it for drain cleaner. So if you go to the drain cleaner section of the supermarket, I just saw it there. It was called, I think, Red Devil Lye. Red Crown, Red Hot Devil Lye. Maybe this is the best. They're all the same. They're all sodium hydroxide. And so just drain cleaner. Sodium hydroxide is a powerful base and reacts with help clear. Also hair, dissolve thing. So you can buy like sodium hydroxide. Also, do you know what else you can buy at the supermarket? Milk of magnesia. Have you ever had milk of magnesia? Yeah?
Disgusting.
It's disgusting, right? I've had it too. It's like a paste, like a solid kind of pasty thing, like chalky. Is that how you recall?
They also something similar to when they do CAT scans.
Yeah, right. Barium hydroxide.
That's disgusting.
Barium sulfate. Barium sulfate when they do CAT scans. I've had that too. They're very similar.
Yeah.
The pasty stuff. Milk of magnesia. Do you know what milk of magnesia is? What's the ingredient in milk of magnesia? That's what I want to know. Milk of magnesia ingredient. It's for stomach issues, if you have stomach issues. See the active ingredient there. Maybe we can see what it is. Active ingredient. Do you see the active ingredient there?
Magnesium hydroxide.
Magnesium hydroxide. So you can buy two hydroxides at the supermarket. You can buy magnesium hydroxide and you can buy sodium hydroxide. So let's say you ran out of lye, but you did have some milk of magnesia. You didn't like the way it tasted anyway. Could you dump that in the drain? And would that work as a drain cleaner? What do you think? Yeah, it's worth a try, probably. Although it's kind of a pasty solid, so a pasty solid, you probably have solids jamming the drain anyway. Or on the other hand, let's say you had some lye, but you ran out of milk of magnesia. And let's say you needed some milk of magnesia because milk of magnesia didn't work. Could you use the lye instead of milk of magnesia? Because, magnesium hydroxide, sodium hydroxide, they're both hydroxides. They're both the same thing, right? They're both bases. And so if you ran out, you just take some lye instead of the milk of magnesia, you'll be fine. There's sodium hydroxide, hydroxide and magnesium, same thing. Would you do that?
No.
No. Yeah, you wouldn't do that. So there's something called chelation therapy. Chelation therapy is for heavy metal poisoning. So the chelate is something that, the chelation is claws, so something that bites onto lead. And lead is reactive, so especially to certain proteins, like sulfur-containing proteins and other things. Lead is pretty reactive to those lead ions. And so the chelates, what they do is they grip onto the lead so they can't react with other things, disabling the lead from reacting with other stuff. So chelating agents bind lead in soft tissues and are used in the treatment of lead poisoning to enhance whatever. You want to get your blood levels down, BLLs, blood lead levels. There are two drugs that are used for chelation therapy. This is a weird anion. It's called ethylene diamine tetraacetate, EDTA, and it's a big anion. And so the two drugs are calcium EDTA and sodium EDTA. So two drugs are offered. EDTA is the chelating agent. That's what binds the lead and disables the lead. Which of these two drugs is more aggressive, do you think? Calcium EDTA or sodium EDTA? Sodium EDTA would be more aggressive? Yeah?
Maybe calcium.
Or maybe they're the same. I mean, it's EDTA, EDTA is EDTA. It's the same thing, isn't it? Like sodium hydroxide and magnesium hydroxide. Yeah. Milk of magnesia. Same thing, right? No, you wouldn't treat these the same. Which one do you think is more aggressive for hydroxide? You're saying if you're going to clean your drain, which one do you think is a better drain cleaner? Sodium hydroxide or magnesium hydroxide? And why would that be? Do you know the solubility rules for hydroxides? Hydroxides are all insoluble except for group 1.
Plus calcium.
Yeah, calcium strong. Magnesium is not one of the exceptions. So sodium hydroxide dissolves in water, no problem. If you have pellets of sodium hydroxide, dump that down your sink, flow some water, and the sodium hydroxide will go to sodium hydroxide aqueous, freeing up the hydroxide. Now the hydroxide can attack whatever is clogging the drain. The sodium ions aren't going to do anything. The sodium ions are going to be spectators. The hydroxides are going to react. However, magnesium hydroxide is what we call insoluble. And so this is why it tastes awful. I mean, it's just a paste. So what they do is they get a suspension. It's a very pasty liquid. It's pink usually, with food color. Magnesium hydroxide is white. And then they, let's look at if they have some images of milk magnesia. See if we have some of them, maybe not the label. Maybe color? Oh, this is white. Do you see how pasty that is? That's because it's insoluble, so they just make it kind of a suspension of the stuff. The stuff I had, it was pink. this is it. Can you see it's inside? Look how cloudy. That looks like a precipitate in there, doesn't it? And this is what we call suspension. Suspension is got a bunch of white solid. And this is why you can drink this stuff. You can drink this stuff, it's not going to kill you. Why? Because this is what we call a weak base. This is what we call a strong base. A weak base like this, is not going to supply that much hydroxide because this is pretty insoluble. This is going to be a lot less reactive. The strong base is going to provide lots of hydroxide. It's soluble. So which drug do you think is going to be more aggressive? Sodium EDTA or calcium EDTA? Sodium EDTA should be more aggressive, right? Because the EDTA will be free, versus calcium is going to kind of stick onto the EDTA and prevent it from reacting as much.
But under like that idea, right? Wouldn't calcium hydroxide be theoretically just as aggressive as that?
Yes, right. So calcium hydroxide is fine. Barium hydroxide, calcium, barium, and strontium hydroxides are considered strong bases, not weak bases. Magnesium hydroxide is a weak base. Sodium hydroxide is a strong base. So the strong bases are soluble hydroxides. And so barium hydroxide, you do not want to drink that stuff. It's going to cause a lot of trouble. Well, anyway, why do they have two drugs? Well, they had more aggressive one for severe lead poisoning where they have to bring the levels down quickly, and they have less aggressive. So the more aggressive one is sodium EDTA. The less aggressive one is calcium EDTA. This is for severe cases. But anyway, sodium EDTA, of course, should not be administered to children because it's much more aggressive. Right? So chelating agents, especially those intended for use in children, should be effective. And so that would be calcium EDTA. And so let's take a look at the case report here. Texas. In February 2005, a girl aged 2 years who was tested for blood lead during routine health surveillance had a capillary blood lead level of 47 micrograms per deciliter. A venous DLL of 48 micrograms per deciliter obtained 12 days later confirmed the elevated blood lead levels, BLL. A complete blood count and iron study conducted concurrently revealed low serum iron levels and borderline anemia. On February 28, 2005, the girl was admitted to a local medical center for combined oral and intravenous chelation therapy. The patient's blood electrolytes at admission were within normal limits. Initial medication orders included intravenous sodium EDTA and oral succimer. Oral succimer, an agent primarily used for treatment of lead poisoning. The medication order was subsequently corrected by the pediatric resident to intravenous calcium EDTA. At 4 p.m. on the day of admission, the patient received her first dose of intravenous calcium EDTA. At 4:35 p.m., she was administered 200 milligrams of oral succimer. Her vital signs remained normal throughout the night. At 4 a.m. the next day, a dose of intravenous sodium EDTA instead of calcium EDTA was administered. An hour later, the patient's serum calcium was decreased to 5.2 milligrams per deciliter. EDTA loves calcium as well. Normal values would be 8.5 and 10.5, so she was at 5.2. At 7:05 a.m., the child's mother noticed that the child was limp and not breathing. Bedside procedures did not restore normal cardiac rhythm, and the cardiac resuscitation code was called at 7:25 a.m. The child had no palpable pulse or audible heartbeat. Repeat laboratory values for serum drawn at 7:55 a.m. indicated that the serum calcium level was less than 5 milligrams per deciliter, despite repeated doses of calcium chloride. All attempts at resuscitation failed, and the girl was pronounced dead at 8:12 a.m. God, so that was like at 4 p.m. and then by 8 the next day. This is pretty tragic. Pennsylvania, a 5-year-old boy 53-year-old woman in August 2003 in Oregon, etc. There are a whole bunch of these, unfortunately. And so people mistakenly using sodium EDTA instead of calcium EDTA because they sounds the same. You know, what's the difference, right? Uh-huh.
This is going on a tangent here, but have you ever heard of a chemical called BPA?
Yes. Bisphenol. Yeah. BPA.
Yeah, there was an article that just came out about how
There's been so many articles about BPA and hormones and that kind of stuff.
this is in quotes.
I'm sorry?
It's in quotes, like that's what you're saying.
Yeah, there's a whole bunch. There are a whole bunch of things. If there's BPA in clothes, then you're going to have higher blood levels of BPA. And then for stain, you know, they have stain-resistant garments. The other big thing is BPA was a big thing a few years back, and the next new thing is PFAS. Have you heard of PFAS? PFAS is the next thing. We'll look at that in a minute, but basically this is a CDC report. Do you know what their recommendation is? The recommendation is do not stock sodium EDTA in the hospital. They recommend to remove all sodium EDTA out of the hospital. That way, this mistake won't happen. So that would be like, okay, at the supermarket, we're going to remove all Y, you know, in case somebody mistakes Y for milk and magnesia or something like that.
Do they use the sodium for other stuff?
They use the sodium to rapidly bring down the lead levels, and so they do. It's for like people who are who need a more aggressive treatment because they're suffering from damage that's being caused by high lead levels, and so they do use it. But they're saying it's worth sacrificing that to make sure that this kind of mistake doesn't happen. So it sounds similar, and a lot of people don't have no idea, you know, what's the difference, you know, between like sodium hydroxide and magnesium hydroxide, or, I mean, obviously they're different names, but chemically, what's the difference? BPA, you know, most people don't have to worry about this because BPA was very common in plastics. And so now when you buy a plastic water bottle, everybody is curious. They want to see BPA free on their plastic water bottle. Otherwise, they're thinking they're getting a little bit of BPA with every drink. And the BPA has some harmful effects, so this is why people worry about it. But bisphenol A, BPA, it's found in polycarbonate. Polycarbonates are very tough. It's like, this is polyethylene thing, but polycarbonate is a very rigid one. It's called Lexan, it's called, or other ones. I have some polycarbonate water bottles. They all contain BPA. And then people worry about BPA in wrappers and food things. And so they come up with a new one. You know, BPA is like something to make the plastics, but
And that comes with synthetic clothing as well.
yeah, probably if it's made out of polymer.
Polyester.
Yeah, polyester. So yeah, you got to worry about that. At least you're not drinking or eating it. So maybe the levels are not too bad. But BPA was big. What was it, a couple of years ago? The next one is PFAS. So PFAS they use in like they put in paper for cooking, you know, this kind of stuff. It gives it like that oil or resistant, water resistant coating on paper and other things, on clothing, a whole bunch of things. But now they're finding PFAS everywhere. They're finding it they're finding it in things like fertilizer. You know, it's getting everywhere. It's like perchlorates in Nevada. You know, they find perchlorates everywhere because of the perchlorate manufacturing plants there. Well, the same thing with PFAS. They're finding it everywhere because these are chemicals that are formed when they put Teflon coatings on things. So you have Teflon coated pots or frying pans or whatnot. And so they find it in water. They're finding it everywhere. It's surprising. In fact, so right now there's a whole bunch of effort going into eliminating PFAS from the environment. And so every issue of C&D News recently has been about PFAS. Here's this. I remember this. This happened a while ago. You have to watch out when you mix chemicals. Like bleach is a good oxidizer. You mix it with certain things. So there's a manager who was cleaning up the spill. Died. Okay, I guess they took it off the front page here, but. So they're finding PFAS levels in gymnasts. Did I tell you about that? And so they have the pads that have like a fire retardant coating on them, and so the gymnasts have a higher blood level of PFAS. We'll get to that. Persistent pollutants like BPA, you don't have to worry about as much anymore. A lot of these fluorinated compounds were thought to be kind of wonder chemicals. But sometimes these wonder chemicals turn into big problems like Teflon. And Teflon's so reactive, people thought it was safe. But then there's all this PFAS stuff now. So a growing number of communities around the world are discovering that they have a problem with exposure to per and polyfluoroalkyl substances. PFAS. To help manage PFAS contamination, researchers affiliated with the Global PFAS Science Panel called out key knowledge gaps that need to be addressed. The biggest question concerns the quantity of PFAS produced and where they are used. So there's a whole bunch of stuff going on. And then there was the PFAS versus BPA. I just saw that article there. So those are things you just have to avoid. It's in water. All right, other questions?
Can we take a look at 77?
Aluminum shavings are dropped into a solution of copper 2 nitrate.
Mm-hmm.
Okay, aluminum is just aluminum solid plus copper 2 nitrate, which is aqueous. So this is the A plus BX pattern. And so we're going to form aluminum, nitrate, and copper. So aluminum nitrate, what's the formula for aluminum nitrate?
NO3.
How many NO3s do we need? 3, correct. Aluminum's 3 plus, nitrate's a 1 minus, and then copper metal. And so when we compare aluminum, this one we probably don't need the activity series. Which one's a more active element, aluminum or copper? More reactive. Copper? Aluminum or copper? Maybe that's a tough one. Both are fairly unreactive, but aluminum is actually a lot more reactive. What makes aluminum unreactive like this, is aluminum stays pristine. But the reason why is it forms an oxide coating on here. And this oxide coating is pretty impermeable. In other words, the structure of this forms a nice impermeable layer on top versus like rust. Rust is very porous and it forms a very permeable layer. And so when we look at rust, iron oxide, iron 3 oxide, it doesn't form a protective layer. And so iron just continues to rust. With aluminum, which do the same thing, but the oxide coating on this is very tough. And so it helps prevent it from reacting. But otherwise, if you remove the oxide coating on it, then aluminum is very reactive. And so aluminum is more active. And copper is less active. And so we have reaction here. Now balancing this is going to be a bit more tricky. Because here we have 3 nitrates, here we have 2 nitrates, so they don't balance. So how can we get the nitrates to balance? We just cross multiply it. And so if I have 3 nitrates over here, then what I'm going to do is I'm going to triple this. If I have 2 nitrates over here, I'm going to double this. And so it's going to give us a common factor 6. So I'm going to have 6 nitrates here, 6 nitrates here. So it's going to work out. And that's going to give us 3 coppers and 2 aluminums. So 2 aluminums, 3 coppers here. And this would be the complete equation. What would the ionic equation for this be? Here. Why don't you work on and tell me what the ionic equation is going to look like for that?
It depends.
Okay, we'll get started again.
I understand how it can't be a different class. I need to take one of them over one of the seminars or something. If I'm going to take a different transfer.
Yeah, it's I know the timing because if you want to take 1A, then you're out of sequence. And so it means organic is going to go over 1 semester. So I understand. 1B is offered over the summer, though. There's no problem with that. All right, for the test, what types of reactions are we going to have? We're going to have element plus element. That's a compound. That's what we call the combination, or the compound decomposes into an element plus an element. That would be the reverse of that. That would be called the decomposition. So compound can be decomposed into the element. However many elements there are. 3, combustion reactions. This is combustion of organics. CXHY or CXHYOZ. This forms CO2 in water. Then we're going to just have your standard single replacement reactions. And your standard double replacement. Were you able to do the chart? Have you tried any chart method? Did that seem pretty straightforward, or the chart method? No?
I need a little bit more time.
The chart? Okay. So on this test, I'm not going to have any chart method. And so others would be the chart method and aqueous ammonia. We'll skip. Aqueous ammonia I'm going to talk about in the lab. And so the chart method and aqueous ammonia we'll just have during the final exam. But what you want to focus on are, you just want to focus on like just your basic double replacement and single replacement and combustion reactions and combinations. Nothing tricky. So it'd be similar to the homework problems here. If you could do the homework problems here, then you should be fine with the test.
How would the distribution of the exam, like, let's say you have all 100% of the exam. Out of all the chapters, like, what percentage of each would you say would be?
I try to do a fairly even distribution, points wise. And so, just
So, for example, have one chapter more than the other.
not really.
I'm talking about the chapter 9 questions.
Yeah, 8 and 9 I can combine together. So that's,
Those are review those questions.
yeah, if you could answer the 8 and 9, but did 9 have the complete equation, ionic equation in total? Net ionic equation?
Just the net.
Just the net ionic? Yeah. Well, you're going to have to write those 3 equations, complete, ionic, and net ionic. So be able to do those for these. Okay, other questions?
For the combustion equations, is the CXHY, the products, are they different?
No, these both yield the same products. And so the other reactor will be plus O2. And this is going to produce CO2 plus H2O. CO2 is a gas, H2O is a liquid, O2 is a gas. And so all you have to do is add O2 to either, and then you're going to form CO2 and H2O. And so this is mainly an exercise in balancing. How can you balance it? Because we know what the products are, and we know what the other reactant is. Now, you aren't going to have to know organic nomenclature. So, like, everybody should know methane, but some of these others, like, you don't necessarily need to know the formula, like butane, propane, ethanol, methanol, those types of things. It's going to be a lot of questions. So if you can bring a Scantron, that would be helpful. Let's see. So it's something like this, right? Some nomenclature. The nomenclature was 2 parts, this test. The first part, which is the nomenclature, is no calculator allowed. And then you have to turn this in, then you can use your calculator. This is part 2 here. So after you finish part 1, you can start part 2.
Is this like a good gauge of what my midterm's gonna look like?
Yeah, your midterm is going to look like this. So a lot of questions. This one is 52, but I don't know how many years we'll have. A lot. Maybe more, maybe less.
Just like an example.
Yeah, this is an example, except this doesn't have reactions in this because
Yeah, it's on canvas.
I had a lot more. I did a lot more this particular semester with reactions. I decided not to do that much this term. So we'll just keep it basic. These are kind of the basic reactions here. So some simple patterns, element plus element. One element loses the left side and of the periodic table. One element gains the right side. In combustion, single replacement, double replacement. Nothing tricky. And so it should fit one of those things. So if you can bring a Scantron, that would be great. One of the what's that?
How would we?
Do you guys know the Scantrons you can get at the bookstore or the library? Do you guys have any Scantrons? You need this form here. It's going to have A, B, C, D, E, F. See if I can get a better image of this. You can buy it like a pack of 6, or you can buy it individually from the bookstore or the library. Library, I think they only sell individual Scantrons. It doesn't matter if you have the numbers 1, 2, 3, 4, 5, or the letters A, B, C, D, E. Either one's fine. Okay. I don't know how much, we're not going to have all of chapter 10 on the test. Take a look at chapter 10 here. That's pretty much chapter 9. There are a few more things I'm going to say about chapter 9 in lab.
Well, yeah, the lab tomorrow, we have 2 labs and a hybrid. What does that mean?
Well, it means we're going to do little bits and pieces of the labs. We're not going to do the entire lab. We're going to do parts of each lab. We're going to just be looking at different chemical reactions in lab. And so it means that I'm just going to do some reactions that I think are.
So those are going to be hands-on.
Yeah. Yeah, you should. That's right. This will be the first official goggles lab. You'll need goggles. You can bring gloves if you like. Nitrile gloves are handy. And make sure a lab coat is always good. And then shoes. Make sure you have shoes, no sandals. Okay. Chapter 10 deals with quantity relationships in chemical reactions. We call this stoichiometry. Sure. So we want to deal with amounts, how much. And like this is a balanced chemical equation. So this is typically read in 2 ways. One, 4 molecules of ammonia plus 5 molecules of O2 yields 4 molecules of NO plus 6 molecules of water. So this is combustion of ammonia, and it produces nitrogen monoxide, nitric oxide here, and combust ammonia. You aren't going to have this kind of combustion reaction. When we combust nitrogen, we form oxides of nitrogen. When we combust carbon, we form oxides of carbon. So it's not that difficult to kind of figure out what we're going to make. The difficult part is which oxide of nitrogen do you form. Usually nitric oxide is very common when we do combustions like this. Eventually that nitric oxide gets converted to nitrogen dioxide. But one way of visualizing this reaction is by molecules, but we don't go by individual molecules. We go usually by moles. So this would be 4 moles of ammonia with 5 moles of O2 molecules. So just an enormous number of molecules yields 4 moles of NO plus 6 moles of H2O. So this is called the mole ratio or the molecule ratio, depending on what scale we're doing it. But typically we do it on the mole scale. So it's a lot. But both of those are abstract because it's hard to measure out molecules. If you wanted to measure out 4 molecules, how would you do it? It's not so easy. If you want 4 moles, how do you get 4 moles? Getting 4 moles is going to be more difficult. But nonetheless, we have the quantity relationships here. And so this is a 4 to 5, 4 to 6 ratio. And we can do calculations here. So the types of calculations we do is, let's say I have 308 molecules of ammonia. How many molecules of O2 do I need? Well, then I have this is called the molecular mole ratio. And so I go back to the balanced chemical equation and I see it's 5 to 4. 5 moles of O2 for every 4 moles of ammonia. And so it's a 5 to 4. And so this tells us I'll need 385 molecules of O2 to react with 308 molecules of ammonia. And so this is stoichiometry here. But since we rarely work with molecules, we use moles. So if I had 308 moles, although that would be huge, it's a 5 to 4 ratio. It would be 385 moles of O2. And so this is typically what we get from the balanced chemical equation. 5 moles of O2 for every 4 moles of ammonia. And we can get other ratios as well. We'll flip those over. So those are what we call the mole ratios here. And this is a stoichiometry map. And so in the heart of stoichiometry, we do a mole of A to moles of B conversion. A does not need to be reactant, and B does not need to be product. It's just a moles of A to moles of B. And to do that, we need the mole ratio from the balanced equation. And so this is the main center of the stoichiometry map. And so you can do very simple problems like this. If you have 3.20 moles of ammonia, how many moles of water are produced? Water would be a product in this case. We look at the balanced chemical equation and we see 6 moles of water produced in that equation for every 4 moles of ammonia. And so this gives us our mole ratio. So we do a mole to mole conversion, moles of ammonia to moles of water using the mole ratio. Here's the mole ratios here. This is a combustion reaction here. This is methane, kind of like methane except 2 carbons. So 2 of these plus 7 of those plus 4 yields 4 of these and 6 of these. Here are our mole ratios here. And so we can relate any of the 2 quantities. So we can say for every 7 moles of O2, we can get 4 moles of CO2. For every 2 moles of methane, we get 4 moles of CO2. So, but moles are somewhat abstract. And so this mole ratio, we don't really do these kind of calculations all that much. They're fairly straightforward, but the thing is, there's no mole meter. So how do you measure out how many moles we have? And so typically we don't do much with this. We do much more with this, or mass. And so this is the heart of the stoichiometry. This is mole to mole conversion. But what we're going to do is we're going to start off with grams. And so we have mass of A goes to moles of A, moles of A goes to moles of B, moles of B goes to mass of B. So this is your standard stoichiometry calculation here. So let's do that here. So mass of A goes to moles of A, moles of A goes to moles of B, moles of B goes to mass of B. We can also branch here, because if we know the moles, then we can use Avogadro's number, which is N sub A, 6.022 times 10 to the 23rd, to get the number of particles, whether they're molecules or what formula units. The same thing here. So there's branches here that we can go down if we want. But the main stoichiometry calculation is this one here. as we go across. And so let's take a look at combustion of methane as an example. So methane, do you know the formula for methane?
CH4,
And so if I say combustion of methane, what do you react methane with?
O2 gas,
O2, and what does it form?
CO2 gas plus H2O liquid.
Yeah. And so you have to know it reacts with O2 gas and it forms CO2 gas and H2O liquid. And then we need to balance this. And so the way I balance this is I have one carbon, and then 4 hydrogens means I'll need 4 hydrogens over here, so I'll have to multiply this by 2. And then let's take a look at what's happening with oxygens. I have 2 plus 2 gives me 4 oxygens, and that means I'll need 2 O2s. So a question might come up, you know, for every pound of methane gas you combust, for every pound of methane gas you combust, how many pounds of CO2 are formed? That would be stoichiometry. So let's say I combust 1 pound of CH4 is going to yield how many pounds of CO2? So I'm going to just say 1 pound. Let's say exactly. If I combust exactly 1 pound of methane, how many pounds of CO2 will I form? Well, if I combust 1 pound of methane, don't I form 1 pound of CO2? It's a 1-to-1 ratio. And the answer is no, it isn't. It's a 1-to-1 mole ratio or 1-to-1 molecule ratio, but the molecules weigh different amounts. So methane actually weighs a lot less than CO2. CO2 is a lot heavier because oxygen atoms are a lot heavier than hydrogen atoms. Hydrogen atoms just weigh 1, whereas oxygen weighs 16. And so CO2 is a lot heavier. And so the mole ratio here, or the molecule ratio, is going to be different from the mass ratio. But I'm not going to calculate the mass ratio. What we're going to do is we're going to use stoichiometry to figure it out. And so if I start off with exactly 1 pound of methane, then what I want to do is I want to convert that to moles of methane. And so I probably want to go from pounds to grams. And so let's do that. I'll go 1 pound of methane, and do you know how many grams there are in a pound?
453.5.
Okay, we'll just do 453.6 grams per pound. And so that gives me a gram. So I have about 454 grams of methane. Okay, then I'm going to do gram to mole conversion. The gram to mole conversion is very common in stoichiometry. What do I need to do the gram to mole conversion? I need the molar mass. And so the molar mass of carbon is 12.01. And then 4 hydrogens is going to be 4.04. So that's going to give me 16.04 grams per mole. And so 1 mole of methane weighs 16.04 grams. So the grams of methane cancel, and that leaves us with moles of methane. Okay, now I'm in the heart of the stoichiometry math, and here I can do a mole-to-mole conversion. And so I see 1 mole of CO2 is produced for every 1 mole of methane combusted. So I'll write that here. 1 mole of CO2 is produced for every 1 mole of methane combusted. So this is going to give us the moles of CO2. And then I need the molar mass of CO2. Carbon is 1201, and then I have 2 oxygens, which is going to be 32.00. And so this is going to give me 44.01. And so a mole of CO2 weighs 44.01 grams. Quite a bit more than a mole of methane. A mole of methane only weighs 16 grams. And so even though they're in a 1-to-1 ratio, they weigh totally different amounts. And the moles of CO2 cancel. And so if I were to combust 1 pound of methane, how many pounds of CO2 are produced? So let's go ahead and calculate that. 453.6
divided by 16.04 times 44.01.
Oh, there's one more thing. I probably don't want to leave this in grams because I'm starting with pounds. I'm calculating grams, 1,244 grams. I probably should convert that to pounds. So let me add one more step to this. And that's 1 pound is 453.6 grams. In fact, I just cancel these out here. So what I end up with is 2.74. Okay, how many sig figs am I allowed? I'm allowed, if I call this infinite, exactly 1 pound, then I have 4 sig figs here and here. So I'm allowed 4 sig figs here. 2.737 pounds. And so this is going to round to 2.744 pounds of CO2. So for every pound of methane you combust, you're going to form 2.7 pounds of CO2. So this is stoichiometry. This is a standard stoichiometry type problem, mass to mass conversion by going through moles. And so let's take a look. Another example here. How many grams of oxygen are required to burn 3.5 moles of liquid heptane? Heptane C7H16. So why don't you calculate that now? So doing the combustion of heptane. So if I burn 1 pound of heptane, would I form 7 pounds of CO2? No, this is not a mass ratio. These are mole ratios. And so you'll have to calculate the molar mass of heptane. Molar mass of CO2, I just read that up there, 44.01. But what would the molar mass of heptane be? You got it? 100.2 grams? Okay, I want pounds though.
Oh. 0.221.
0.221 pounds. £0.221, that's a lot less CO2 than methane we produce on a pound basis. Yeah, double check and see. Let's see what else other people get. You would do mole to mole. And so here we're going to do mass to mole. So So if we have 1 pound of heptane, C7H16, then we convert it to moles. 1 mole. Actually, we can't. Yeah, we convert it to grams. And then moles. Well, it depends on what we're after. What are we after?
The product, how much CO2?
Yeah, so we need to know the mole ratio between heptane and CO2 from the balanced chemical equation. So what is the mole ratio?
7 to 1.
7 to 1. And then what?
They convert that back to grams.
Yeah. What's the molar mass of CO2? We had it up earlier. Let's put it back up there. And then back to pounds.
1 pound.
453.6 grams. And what did you guys get?
Three point oh seven
3.07?
oh seven. Where's your conversion function?
3.081? 3.075? Let's take a look. 453.6. It depends. Some people might carry extra digits. I mean, if you know it as 453.59, you could use that. It's actually better. Because you've got less round off there. It wouldn't change because we just cancel it out. So you're right.
I didn't add the fifth digit in the grams.
I just calculated. I got 3.0736. Anybody else? You got that? All right. If I get 3.0736, then I would round it 3.074 grams, or not grams, pounds of CO2. So for every pound of heptane, we get about 3 pounds of CO2. A little more actually than methane. So this is one of the reasons why, the city of LA, did you know the city of LA is going to ban gas stoves and gas ovens? So it's going to go all electric stoves and electric ovens. Electric oven most people have, but a lot of people like gas stoves instead of electric stoves. I grew up using a gas stove, so it's going to be weird to switch to electric. For me, it would be hard. What's that? Yeah, I didn't. I've sold their stove before, but I just don't like them. The induction ones are cool.
Is it crazy?
Yeah. Yeah, induction and boils water really fast, but. And then they have these induction ones where you can cook different things at different temperatures all on the same surface. But so induction might be okay, but just a regular electric, I don't think I can handle that.
It's kind of stupid. induction is
One
when
pound
it
equals
doesn't get hot,
154
it just
grams, okay, or do you want it 453.6?
453.6, but that one you don't have to memorize. I'll give you that one. Yeah. I'll give you the grams to pound conversion and one other one.
they put it
The other one,
in the gram.
the other one would be liters and gallons. 3.785 liters to gallon.
Wait, what are you asking? I was just asking about the
That's so
conversion.
cool. Oh my god. That'd be kind of scary. No, because that's the thing. It doesn't get hot. The induction stove was inside the grill, and the induction stove doesn't get hot.
What if you keep it?
No, but like you have it during the camera, so it knows when there's a camera. As opposed to it doesn't know. Is that what you're saying?
It only works
I don't know how like induction so cool.
Likewise, we can relate this to anything in the equation. We just change the mole ratio, so we can figure out how many pounds of oxygen we need. You know, so why don't you calculate how many pounds of oxygen you need to combust 1 pound of heptane next. And so, how many pounds of O2 are required to combust 1 pound of heptane?
How many grams instead of CO2?
She's probably just have to switch the mole ratio. Right?
Yeah, all you
Put
do
11 in there.
and the weight, right?
Oh, wait, yeah.
I don't think. Let's change. I want to do it. Is it still 7?
No,
No.
it's oxygen.
Tracy, you got this. Do it, but then don't ask any questions, okay? Is it oxygen?
I'm sorry? Per 1 pound of heptane. Not 3.5 moles, but 1 pound of heptane. Let me know when somebody gets it. 1.756? What did you get, Tristan? You got something different? 2.716.
Oh, no, I was doing the first problem that you did.
Oh, okay. All right. And somebody else confirm it. 1.7 pounds of oxygen for every pound of
I think I'm way off.
heptane. What did you get?
19.31.
19.31. Yeah, that seems a little high. What did you get? 3.512. You got the same? 3.512.
Yeah, that's what I got.
That's what you got? Okay. 3.512 pounds. This is why we don't do balanced chemical equations using mass ratios. If we did it using mass ratios, then we would have 1C7H16 plus 3.512 O2s. And so this would be a mass ratio here. So this is going to be pounds, grams, kilograms, whatever. This is going to yield 3.074 CO2s. And how many waters? How many pounds of water would we form? There are two ways to calculate the pounds of water. One way is we can take advantage of the conservation of mass. And so I total up the weight. Altogether, I'm going to have 4.512 pounds of reactant. That means I need 4.512 pounds of product. So I could just use the conservation of mass, or I could use stoichiometry, and I should get the same answer. So how many pounds of water will I form? Well, it's going to be about 1.5 pounds of water, but can you calculate it? Let's see.
1.438.
1.438.
So this would be mass ratio. We could use any mass units here. Pounds, grams, kilograms, whatever. But we never write an equation with a mass ratio because it's just messy.
This is why we prefer mole ratios, even though moles or molecules are a little difficult to measure versus mass. Mass is easy to measure. And since we're in stoichiometry, we're curious about mass relationships usually. And if we wrote the equation as a mass ratio, it'd be hard to figure this out without doing calculations. But if we write the equation as a mole ratio, it's a lot easier to figure out. And so the mole or the molecule ratio is going to be C7H16 plus 11O2s yields 7 CO2s plus 8 H2Os. And so this is why we're always going to have to do extra steps here, because the mole-to-mole conversion is what we want. It's the easiest versus a mass-to-mass conversion. Mass-to-mass conversion is a bit more hassle with this. What do you think of stoichiometry?
Easy.
It's easy. So this is just more mass to mass. How many milligrams of nickel 2 chloride are in a solution at 503 milligrams of silver chloride is precipitated in reaction with silver nitrate and nickel 2 chloride solution? This one seems a bit more complicated. Why don't you try this one here? So you got 2 silver nitrate. What's the formula for silver nitrate?
AgNO3
2 AgNO3
plus nickel 2 chloride, so it's NiCl2.
NiCl2.
And then that results in 2 silver chloride, so 2 AgCl plus NiNO3 too.
Okay, let's get the states for these here. So, did you figure it out?
Yeah.
Okay. What's the state of this?
Aqueous.
Aqueous. All nitrate salts are soluble. This one?
Also aqueous.
Also aqueous. Chlorides, bromides, and iodides are all soluble except for
Group 1, group
the other way. They're all soluble except when they're insoluble, then we use that one. But when they're all soluble, it's chlorides, bromides, and iodides are all soluble except for
lead, mercury, and silver.
yeah, silver, lead, and mercury. So this is not an exception, so it's soluble. Chlorides, bromides, and iodides are all soluble except for silver, lead, mercury. So this is one of the exceptions. So this means it's insoluble, so it's going to precipitate. And then all nitrates are soluble, so this is going to be aqueous. And this one was a bit tricky because they said the reaction was between silver nitrate and nickel 2 chloride. And so that's why we had these as the reactants here. They didn't mention the nickel 2 nitrate that forms, but that's okay. Those are going to be spectators. If we look at the net ionic, actually, let's take a look at the net ionic for this. If we look at the net ionic, it's only silver and chloride. The nitrate and the nickel are spectators. And so if we were to do the net ionic equation, then we'd see that we'd have 2 silver ions combining with 2 chloride ions to form 2 silver chloride solid. And here we've already cut it down. The silver plus chloride yields silver chloride solid. And everything else is a spectator and cancels out.
But we are going to do the ionic or the net ion equation because for stoichiometry, it's easiest to just go off the CE. And so typically for stoichiometry, we'll just leave it like this. It's a lot easier. So that's good. And so we go from, we want to go from like grams of A to moles of A to moles of B to grams of B. But in this case, we're starting with milligrams. So if we go milligrams, we'll go milligrams of A to grams of A, grams of A to moles of A, moles of A to moles of B, moles of B to grams of B, grams of B to milligrams of B. And so let me know when you have the answer for this. Now, you need the molar mass, though. And so we need the periodic table for this. A nickel is 58.69. Chlorine, a nickel is 58.69. Chlorine is 35.45. Silver is 107.9 or 0.87. 107.87. Okay, we don't need nitrogen and oxygen because they're asking for a nickel 2 chloride and they're giving us silver chloride, so that's all we need. You have an answer? Okay, what did you get?
302.3 milligrams nickel chloride. Nickel 2 chloride.
For the nickel 2 chloride?
Yeah.
Okay, good. Anybody else? What did you get?
227 milligrams.
227? Okay. We'll need some tiebreaker here, not tiebreaker, deciding vote here. Or if you got something different, let me know.
I got something different.
You got something different? What did you get?
I got 182.3.
So we have 3 different answers.
Okay, mine's wrong.
Yours is wrong? All right.
Yeah.
Sorry. Your molar mass is 143. For what? HCl. That's what I got. I got 178.
27 plus 35. I now got 220, 226.
You got 226.6. All right, so we have
So far, this, the two people who got that.
yours is wrong. So it's looking like 227. It is 3 sig figs.
All right, how did you guys do this one here?
There we go, 503 milligrams of
All right,
chloride.
you start off with 503 milligrams of silver chloride, and then you converted it to grams. Yeah, this is what I would have done. I would have gone from milligrams to grams. That is, there are 1,000 milligrams in a gram. So we use.
Yeah.
Then we have the grams of silver chloride, and then we convert that to moles. And 1 mole of silver chloride weighs how much? 143.32 grams. Okay, so the grams of silver chloride cancel, that leaves us with moles of silver chloride, and then moles of silver chloride to what?
Moles of chloride, 1 to 2 ratio.
All right, what's the mole ratio?
1 to 2.
1 to 2. Okay, so 1 mole of nickel to chloride for every 2 moles of silver chloride.
Yeah.
So moles of silver chloride. So this is kind of the heart of the stoichiometry. Grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. And so what's the molar mass of nickel to chloride? 129.5. Nickel to chloride per mole. And so I have grams of B, and then we don't want grams, they want milligrams. So we'll do a milligram conversion here. That is 1,000 milligrams per gram. And so the grams cancel, that leaves us with milligrams. 1,000 will cancel too. And so you got 226 point. We'll do it to 4 sig figs and then we'll round it to 3. 227.4. 227.4 milligrams, which rounds to 227 milligrams of nickel 2 chloride required to precipitate that much. So what I'm thinking for the test, we'll probably just go up to here for the test in chapter 10. Not all of chapter 10. And so you'll just have a standard stoichiometry problem to do. Now, the book loves this thing. They like to do this, millimoles and a millimole to millimole conversion, because they don't want to convert it. But I don't like to do that. I don't like too many variations. I just like the same thing and then just convert it. But you're welcome to use whatever way you want. It's just my personal preference is just always do the gram to mole, mole to mole, and mole to gram conversion, and then just get everything in to those units.
So, chapter 10 will be due on
No, chapter 10, the homework will not be due on the test day. The chapter 10, you just need to let's take a look at the chapter 10 homework problems here. Yes, chapter 9 will be due, and then what we're going to do is we're just going to do mass-to-mass stoichiometry. The percentage yield, the limiting reactant, will not be on the test. And so if we look at, it's just through 10-2. So let's take a look at We'll talk about it though, but I'm not gonna have the full assignment due. And so for preparation for the test, you'll want to do the homework problems. For section 10.1 and 10.2. That's it.
Yeah, I did, number 11, that was brutal.
Number 11. So
Yeah, that one was brutal.
this one's brutal, yeah.
Let's see why.
It's brutal. The molar masses are going to be very large.
Yeah.
Yeah. That's severe to calculate.
Yes.
You know, soaps are produced by reacting fat with sodium hydroxide. So they do this reaction in organic chemistry. Take different fats and react them with sodium hydroxide to make homemade soap. So 10.2, there's a lot of homework problems.
This is very nice. Lots of jokes.
Did you do any others, Gabriel?
Yeah, so,
Lose that or A. And then,
well, I didn't know if we were gonna have chapter. What I wanted to do was do as much as chapter 10 and then just start reviewing like this whole.
Okay, that's good.
But I did stop at 13, so I did, number 9 and 1, all of 1.
Okay. Well, at least for 10.2, they're all going to follow the same format here. And so you'll be okay. Question.
never.
Chapter, so they changed all those. Are you gonna give those ones, or you have to-
Well, for the gas chapter, what do you need to remember?
I mean, it's not that many things, but I was just curious about.
So the combined gas law,
Yeah, the pressure one. And
the pressure conversions, you'll have to know. Which pressure conversions are you gonna have to have memorized? Yeah, ATM is 760 millimeters of mercury. You need to have that one memorized, which is the same thing as 760 torr.
One bar is 1.013 atmosphere.
Oh, actually, it's 1 atmosphere. No, 1 atmosphere is 1.0325. What was it?
I thought it was 1.031.
1031.
Yeah.
1031. 1031.
And then it just goes in different multiples of 10.
And then 14.7 PSI.
Yeah, 14.7 psi in an atmosphere. That one,
One bar is 14.5.
14.5 psi. You don't need to know that. You don't need to memorize that because we can calculate that. But this conversion is a little strange. Let me take a look at the conversions here again.
I should have asked you for them to
Oh, you're just memorizing all those? No. Right, don't memorize all those. What chapter was the gases again? 6?
Yeah.
5? Let's take a look at that.
Maybe it's 4.
4. It'll be
So
4.
we need to know 1 atmosphere is 1.031.
No, you don't need to know that. That's going to be very difficult.
But guess what? I know it because it's the same.
If you already memorized it, it's good. But sorry, you don't have to memorize that. Let's look at the pressure units here. So definitely you need this. 1 atmosphere is 760 millimeters of mercury. That's the big one. And a millimeter of mercury is the same thing as a torr. So you definitely need to know this here. And you'll be okay with that. There are other units up here.
What about the sub-calculation from that combined gas law? You know how there's like an offshoot of that equation for specifically volume?
Oh, yeah. If certain things don't change, you can cancel them out. So usually the amount of gas doesn't change, so we cancel that out. We get that equation. If the pressure doesn't change, we cancel that out.
Oh, so it's actually the same equation?
Yeah, same equation. So every offshoot of it is from this equation.
Okay.
Yeah.
So, can we quickly go over parts per million?
Parts per million? Yeah, we can do that. If you want to remember parts per million, think about parts per hundred first. You know, so if you had 6 parts per hundred, we could call that 6 pph. But we have a symbol for parts per hundred. What is the symbol for parts per hundred? Percent. And so this is 6%. And so everything that we do with percentages, we do the same thing with parts per million. So if we have that, that means 6 out of 100. That's the fractional form. Or the decimal form would be 0.06 out of 1. And so it's the same type of deal. So let's say 6% by mass means that we have 6 grams per 100 grams. So let's say this is 6% by mass A. So this is 6 grams of A out of 100 grams total, which is 0.06 grams of A out of 1 gram total. And so here we have the fractional form. Here we have the decimal form. And here we have just the pph, or the percent. So when we calculate percentage, let's say I had 1 gram of A in 10 grams total. So I get a ratio, 1 gram of A per 10 grams of total. What percentage is that? Can you see what percentage that's going to be? This is going to be 10%. Or you can just multiply by 100%. And this is going to give us 10%. Sometimes the numbers are really difficult. 1.328 grams of A in 3.675 grams total. What's the percent? Yeah, around 33, but all we have to do is multiply by 100%, and then we can get the percentage. All right, and so let's calculate what the percentage there is. So 1.328 divided by 3.675 times 100. 36.13%. Something like 36%. Something like 36.136%. That's more digits than we allow.
All right, if we want to calculate ppm, then it's the exact same thing. Except instead of multiplying by 100%, we multiply by 1 million ppm. So 10% is equivalent to, okay, so we do this, here. What would it be? So I'll just do it. 1 divided by 10 times, actually not times, divided by a million. And I'm going to get 0.000001 part per million. Actually, did I do that? I messed that up. Sorry, I didn't. It's supposed to multiply. You know what it's going to come out to? Actually, let me do this one more time. 1 divided by 10 times a million. 100,000 parts per million. So, parts per million, you just use the same rules. And so if I had 100,000 parts per million, A, then I can write that in different ways. One way I could write that is in fractional form. This would be 100,000 parts of A over a million parts total. Or I could write it in decimal form, etc. And so the way to think about a parts per million is it's exactly the same thing as a percentage, except rather than multiplying by 100%, you multiply by a million. And to convert it into fractional form, rather than dividing it by 100 like we did over there, we divide it by a million, which is going to give us what is the decimal form. So that would be 100,000 divided by a million. We should be able to figure out the 0.1. Actually, that can't be right. Let's screw this up. No, I guess I get it right. Is that kind of what you're asking, or not really?
Yeah, and just, like, I guess an example of parts per million.
Yeah. So did I give you a parts per million question on the test?
You did.
Take a look at that.
And I answered that one like it was weird how much it down in the mercury weights. I got the answer something like 112 pounds.
Yeah, right. 112 pounds. It'd be hard to lift that. Yeah. Do you recall what number that was, the parts per million?
It's the last one. Last one I didn't do.
Well, wait, are you talking about?
Oh, yeah.
Never mind.
Yeah.
Yeah, that's right, 112. So if you were to, it'd be hard to lift. Really hard to lift.
I don't remember what number it was.
Here it is. Pool water having 1 part per million chlorine means 1 gram of chlorine per million grams of pool water. Is that right? Yeah, that's right. It's like, if it were 1%, this is by math. One we have to assume by math. This would be 1 gram of chlorine out of 100 grams of pool, right, if it were 1%. But it's not 1%, it's 1 ppm. So it's the exact same thing here, except that you do 1 gram of chlorine for 1,000,000 grams of pool water.
So this is true. 25 is true. Did you guys already go through this?
Yeah.
I did.
Or what did you get for 1?
Cool.
Did we already do this? No? All right. 1, false. Doesn't have, I mean, it could, but it'd be hard to come up with a hypothesis without first seeing observations, so false is correct. 2, structure. Correct. 3,
True.
True.
true. 4,
False.
isotopes are atoms of an element with different number of electrons. False. Different number of neutrons. 5,
C.
C. 6, true. Correct. 7.
True.
Now, this one's a trick question. Is it really exactly, or is that rounded to 4 sig figs? Is that exact, or is that rounded? It's not. That one's rounded to 4 sig figs. And so if I wanted the number, okay, let's go to just Google it here. 1 liter equals gallons, let's say. Or not, I want the opposite, sorry. Convert gallons to liters. So I'm going to change this to gallons. Gallons. And then go to liters. Imperial liter, US gallon. Do you see it's been rounded?
What about inch to centimeters? So 2.454 centimeters is rounded, I'm assuming?
No, that's exact.
Oh, that's
Yeah, it's weird. That one's always weird. This is why I'm not having you memorize this because you're just memorizing this 4 sig figs.
So would it be false then?
Yes.
Oh, I would have gone.
So there's exactly, no, this has been rounded to 4 sig figs. And so this is false. Is that clear for that?
Now,
All right. 8. 1 cubic inch is equal to how many cubic centimeters?
2.54.
No.
You have to cube 2.5.
You have to cube 2.54.
Yeah, 2.54 centimeters.
No, you have to cube 2.54.
So it's
The number.
Oh,
You have to cube both the number and the unit.
I forgot.
And so what's the correct answer?
A.
A. 2.54 cubed is equal to 16.387. And so A is correct for number 8. Number 9. Which measurement is more accurate?
And
C
Determine.
is more precise, but
You don't
It's
know
so
exactly.
It's C. We cannot determine. A is more precise. Exactly. It's more precise, but we don't know if it's measuring accurately. You know, it has to be calibrated properly. And so you could have the most expensive, the highest precision balance, but if it's improperly calibrated, it's not measuring correctly. So the calibration is important. And this is why, gasoline pumps are very precise. Supermarket scales are very precise, but we don't know if they're reading accurately, even though they're very precise. Because we don't know if they've been calibrated properly. 10. 4 sig figs is correct. It depends on this number here.
Oh, I have a question. I think there's a sig question in there. And it seemed like the right answer was 1 sig fig, but it didn't make sense to me.
There must be a number 11 here. How many sig figs are in the number 0.07?
No, it wasn't that one.
Well, how many sig figs did you get here?
One.
One.
Is it 17?
It was like 15, yeah, it was like something like that.
17. How many sig figs are allowed?
Yeah, so like the product of that is,
I got C.
C is correct.
maybe it was
3.
equal to.
11 is A.
11 is A. 12. How many sig figs are there in 32 degrees?
Infinite?
Infinite. This could be it. A lot of people will say 2 sig figs, but it's not correct.
No, I'm gonna find it, sorry, maybe it wasn't on that.
We'll just finish with 13 since we're out of time. The chemical properties of sodium and sodium ion differ.
True.
That's true. All right, we'll finish this on Wednesday. Go through.